All right, so once again, you are all welcome. We want to begin cost efficiency, which encompasses technical efficiency. So even if you didn't understand technical efficiency, you will be able to use the principle of what we are going to do now to understand. So pay, please, more attention than ever before, okay? So I want to begin by defining what cost efficiency is. There are different names for doing cost efficiency. Now, if you are doing cost productivity, you must know cost efficiency. If you are doing technical efficiency, you don't have to know cost efficiency. However, the knowledge of cost efficiency will help you because it will help you to better understand it. Because cost efficiency encompasses, it includes, it incorporates technical. Another word for cost efficiency is economic efficiency. Another word for cost efficiency is overall efficiency. Another word for cost efficiency is X efficiency. Majority of people do not use X efficiency, but X efficiency is mostly in the world of the stochastic frontier analysis. Those who are undertaking parametric studies, parametric frontier methodologies, they talk about. And when we talk about these parametric frontier methodologies, there are those frontier methodologies where you have to specify a functional form for the production frontier, for the cost frontier, for the profit frontier, or the revenue frontier. You specify a production frontier or any of those frontiers. And then so there's a specification situation you got to go through. You have to make assumptions about the distribution of the error term, and they also assume a composed error. So the error term is made up of two different things. One is inefficiency, and one is the actual random noise. And you have to make assumptions about each one of them. Some of the assumptions include normal distribution, assumptions about the distributions, okay? Normal distribution, half normal distribution, truncated normal distribution, gamma distribution, McFadden, Leontiev, and so many more. But that is in that. So there are three major kinds of parametric, frontier methodology. We have the stochastic frontier method, or the stochastic frontier analysis. You have the thick frontier analysis, and then you have the distribution-free analysis. However, because of certain, difficulties associated with it, especially issues related to misspecifications, parametric assumptions, and very restrictive assumptions, majority rather use non-parametric frontier methodologies, which is made up of the two main ones are the DEA and then the FDH. The DEA is what we've been doing all through, data envelopment analysis. The FDH is the free disposable. It's more or less like the extreme, the restrictive extreme version of the DEA. Today, I want to look at cost efficiency. Remember that we indicated that technical efficiency is efficiency attributable to managers' performance, managerial acumen. So sometimes we even call it managerial efficiency. Now, X efficiency uses cost as the input. And the idea is that a particular firm is going under the world of cost minimization. If you have understood the principle of variant economics, microeconomics, the principle of duality means that whenever there is a cost minimization, then there is a profit maximization. Okay, so those principles are what we'll be using here. But the key essence of cost efficiency is the ratio of the minimum feasible cost to the actual cost. So the minimum cost divided by the actual cost. So the actual cost is the cost you've gotten from the data set. Then based on these, you will now be able to identify the minimum cost. And then everybody will be kind of assessed in relation to this minimum cost. And such an assessment is what leads to the cost efficiency. The cost efficiency we'll be talking about is attributable to the Farrell definition of cost efficiency. And that reflects the ability to produce the current output at the minimum cost, given the current prices. So note, in cost efficiency, two things are given. One, the prices of the inputs are given. Listen well, the prices of the inputs are given. Now, if prices of the inputs are given, then it means that we are in the world of one price fits all. If they are given, then it means they are not changing. Do you agree with that? And if they are not changing, what does that mean? It means you are in which kind of market structure?
Effort competition.
Effort competition.
Okay, so that's where we are. That's where we are. But life is not all that perfect. They are imperfect market systems. And so you come to realize that this assumption was later relaxed. But you got to know that the definition of cost efficiency, the inefficiency associated with the input levels from the cost efficiency, this is split into technical and allocative efficiency. I'll be looking at each one of them as we go on. When you're calculating cost efficiency and you get a score of 1 for a particular firm, it means that firm is cost efficient. And like the technical efficiency, you can also model this cost efficiency assuming variable returns to scale or constant return to scale. Now, I've already told you that there is a test that you do, the test of the returns to scale. Do you all remember?
Yes, please.
There's a test you do that shows particularly that we are operating under variable returns to scale. And that test is the non-parametric test of returns to scale by Semer and Wilson, 2002. You will be doing this. I'll be teaching you in this course where you will do it. So it doesn't matter the kind of efficiency you are doing, whether it's technical efficiency, which means that automatically you are dealing with pure technical and allocate and scale efficiency. Whether it is cost efficiency, okay, which means that I want to show you some of these things instead of talking a lot. Okay, cost efficiency, okay, which means that in principle, so this is cost efficiency, which means that you are now dealing with pure technical efficiency, okay, which is a VRS one, okay, and then you have the scale efficiency, okay, and then you have the allocative efficiency. This is the cost efficiency. Okay. That's the cost efficiency. These two is what gives us the normal technical efficiency under the CRS. Okay. That's what gives us the normal technical efficiency under the CRS. So it doesn't matter what kind of efficiency you are dealing with here. The most important thing is that there is a so that was I just hope that what I showed, okay, you all remember. So let's take a particular example of allocative efficiency. I'll explain all of this using graph, and you will learn how to do this thing also using graph. It's very important you follow me. But we've not really started the intricacies. Allocative efficiency of say 80% means that we could have saved 20% by better allocating our funds towards a cheaper but sufficient input mix. Now, allocative efficiency is not easily interpretable. It's not easy to interpret it. But we'll do our best, and we'll be doing a lot of interpretation of these things here. Okay, so just be ready for that. Now, let's go back to cost efficient. To be cost efficient, always remember that to be cost efficient, a DMU must be able to choose the right mix of. That is allocative efficiency. You should be able to choose the right input mix. And when you choose it, then you use them well. When you are using the inputs well, that is technical efficiency. When you are using the input, so sometimes we say that use the right resources and use them in the right way. Use the right resources. That's allocative. And use them the right way. That's technical. So try and understand cost efficiency. Cost efficiency is the allocative part, dealing with the inputs that you are using, the mix of the inputs. Why would you want to combine a professor with a cleaner when you could have combined a professor with a researcher? Okay, so sometimes the mix is important. The mix have got their prices fixed as well in this context. So we are going to look at each one of this. This is the model for cost efficiency. Look at it carefully. This is a model. This is a model of cost efficiency. This cost efficiency was by Farrell, but it was formalized by Fair et al. 1985. Look at the model. It says that minimize with the intention of getting the lambda, which is the coefficient, or the multipliers. Okay. Minimize what? The total cost, which is C. And the total cost is the weighted sum of the inputs and their prices. So this is the input price for the DMU under evaluation. And this is the input itself for that same DMU. The DMU under evaluation. Now, how do I know that is a DMU under evaluation? Remember, each DMU is evaluated once at a time. Now, the DMU under evaluation, we always add a naught, the 0, to it to indicate that it is that a particular DMU, a target DMU you are dealing with. The W is the price of the input. The X is the input. The summation sign indicates that you have to sum the input price and the input. Does it make sense? You all understand?
Yes, Doc.
Yes, Doc.
So watch here. So let's say that C can be the weighted sum of the input. So let's say that the inputs are 3. And therefore their prices will be how many?
3.
So you have W1, okay, plus W2X2 plus W3X3. These are the inputs. Those are the input. Daniel, don't be answering because your background is noisy. Okay. So you have these inputs, and these make up the total cost of that firm. What I've done is that I've summed them using these things. And that is why that summation is what you have here, WX. This is the total cost. And what you are going to do is that cost is not a healthy thing. So the goal is to minimize the cost. That is the whole idea here. But it's always subject to some constraint because this is a linear programming problem. And so you have the constraint. The constraints are not different from the constraint you knew before from the technical efficiency. Watch it. The constraints are not different from that. Now, when you look at the constraint, this is the input constraint, this is the output constraint, and the last one is the VRS constraint and the non-negativity constraint. Who can tell me the slightest difference in this constraint and then the technical efficiency constraint? Who can sense and tell me what is the difference here?
1 is the output constraint, 1 is the VRS constraint, and 1 is the non-negativity constraint. 1 is the input constraint, 1 is the output constraint. 1 is the VRS constraint, and 1 is the non-negativity constraint. 1 is the input constraint, 1 is the VRS constraint, and 1 is the non-negativity constraint. 1 is the input constraint, 1 is the VRS constraint, and 1 is the non-negativity constraint. 1 is the input constraint, 1 is the VRS constraint, and 1 is the non-negativity constraint. 1 is the input constraint, 1 is the VRS constraint, and 1 is the non-negativity constraint. 1 is the input constraint, 1 is the VRS constraint, and 1 is the non-negativity constraint. 1 is the input constraint, 1 is the VRS constraint, and 1 is the non-negativity constraint. 1 is the input constraint, 1 is the VRS constraint, and 1 is the non-negativity constraint. 1
Who? Who can raise their hand and tell me? What is the difference between this constraint you're seeing here and that of the one for Edwin?
I don't see theta.
Exactly. You don't see theta near what? You have to be clear.
X.
Near X. Or you don't see what near what?
And phi near Y.
Excellent. Very good. Eh? You're smart. You are really a learner. So there's no theta near X and there is no phi near Y. So it is just the normal constraint as it is without attaching any theta to it. This is, but you see, this doesn't give you the cost efficiency score. What you are seeing here is the cost, the total cost, but not the cost efficiency. But when you use this approach, you'll be able to minimize the total cost to a certain point. Let's look at that certain point. If you estimate that cost, you put it down. That cost becomes the actual cost. That cost becomes the actual cost for that firm. But of course, if it is the smaller cost, or did I say it becomes the actual cost? It becomes the minimum cost. Sorry. It becomes the minimum cost for the industry. And so if you solve the Bound model, you're going to get that minimum cost. Because the actual cost of the firm, this firm, the actual cost, you can calculate it. How can you calculate it? Well, you know the actual input of that firm. Let's say it's 10. You know the price of that input. That is 2. Then that firm also has a second input. You know the input is 20. And then the price of that input is 3. So you can take, and those ones are actuals. But the one you are just calculating using this linear programming is the minimum cost. Once you calculate the minimum cost, which is CM, you will now match it against the actual cost, which is C0. Remember, what you are having all here is C0. And so you will also have that one to be C0. So you calculate the minimum cost, and then you now already have the actual cost. The actual cost of the current input of the firm and the evaluation. Once you have the actual cost, then the Farrell, or in this case, the FAIR, remember I told you that, you see, Farrell will call it cost efficiency, FAIR will call it overall efficiency. So the cost efficiency can now be calculated as the minimum, which is the CM on the top here, the minimum cost divided by the actual cost. So it will be CM divided by CO. This is what you have here. CM divided by CO. CM divided by CO. Now, ideally, what you see here are a little bit of difference, but ideally, if we were to go directly, we can say that, you know, one of these, you see, this one is a star. This value here, everything at the numerator is the same as the denominator, but the numerator is a star. The star is indicating as the minimum cost. And then the one below is the actual cost. That is the cost efficiency. And when this value is less than 1, it means that firm is inefficient. And if it's equal to 1, the firm is efficient. Of course, you can split this one into now the technical efficiency and the allocative efficiency. Now let's try and understand this better. In the world of Tanasolis and Patella, which we'll learn later, this is how you define this overall efficiency, also called the cost efficiency. Watch the definition carefully. The cost efficiency, the OE means overall efficiency. The C is cost efficiency. And it is made up of a computation taking into consideration the input, the output, and the input prices. That is why you have the X, the W, and then the Y. Now, the way you write the minimum cost, because these two things are given. The two things in the bracket are given. So the minimum cost given the output and then the input price, that's the minimum cost. And this is divided by the actual cost, which is the price of the input plus the actual input. Now, I told you that it is the cost efficiency is the minimum cost over the actual cost. The actual cost is also the observed cost. That is why you see this one. I just decided to give you these two formulae. So the minimum cost of producing an output, a given output, given the input prices and the technology, that is the C. Now, this is where it becomes interesting, the decomposition. So the overall efficiency, which is a cost efficiency, can be decomposed into technical, what I told you before, and allocative. And the technical alone can be decomposed into pure technical and scale. Therefore, the cost efficiency can be said to be pure technical, scale efficiency, and allocative efficiency. Now, may I see which of you is doing cost efficiency or cost productivity in a way? Which of you is doing cost efficiency or cost productivity?
Cost productivity, Thelma and Chris.
Don't worry, once you raise your hand, I will know. I just want to know the number of people doing that. Okay. Cost efficiency and cost productivity. Dana, it appears, okay, you are a co-host, so you are not able to use a hand thing. Okay. So, all right. Let all of you should put your hand down except those who are doing cost efficiency. If you are doing cost efficiency, keep your hand up. If you are doing cost efficiency, keep your hand up. Okay, all right. Dana, don't worry, they don't know that they are doing both. When you don't know that they are doing both, that they are doing both. All right, okay, excellent. So now that we know that you should appreciate and understand the fact that you'll be doing a lot of decomposition. So please, cost efficiency is ability to produce current output at a minimum cost. Look at that word current. Current here means given. You're producing the current output at a minimum cost. Keep that in mind. Okay. And allocative efficiency, okay, is the ability to use the input in optimal ratios, given their respective prices. This definition, if you don't take it, you won't understand the allocative efficiency definition. Every input you are having, you sometimes combine the input. Take, for example, a lecturer for a university. The university is a DMU. The lecturer and the computer. So the university has given a computer to the lecturer. One lecturer to one computer. One lecturer to one computer. Now, is the university, are they able to produce graduates, okay, using the two input of lecturer and computer? Are they? And you got to use the input in optimal percentages. So there's a price attached to the lecturer and there's a price attached to the laptop. You got to use them in optimal percentages. So you got to use, if it is one lecturer, 10 computers, then what it means is that you are not able to combine the input and the output efficiently. You're not able to allocatively, efficiently use the input. Because why are you giving one lecturer 10 laptops? It's a waste of money. So there is that misallocation of input. And that is critical. That is what allocative efficiency looks at. So the definition of the allocative efficiency is this. Look at it. This, I am bringing TTT on top of it. Please note something. We can decide to omit the T. So you can see that this is allocative efficiency, and the AE, the allocative efficiency, is equal to something. Watch carefully because this is a little bit tricky. We said it's equal to the minimum cost. Okay. First of all, the cost efficiency, which is the numerator on the top here is the entire cost efficiency. And the entire costs, minimum cost. Okay, the entire minimum cost. What am I saying? The entire cost efficiency is the allocative efficiency times the technical efficiency. So the one on the top here, is more or less, ideally, the technical efficiency. Okay, it's more or less the technical efficiency. But of course, this top part, watch it. The CYW divided by the WX, this part alone is the minimum cost over the actual cost. Do you realize that?
Yes,
Yeah.
please.
So that alone is the minimum cost over the actual cost. Now this part, which is the minimum cost over the actual cost, let me just write something here. Otherwise, you guys might miss it. Okay. Come on. Good. Now, this part here, okay, is the minimum cost over the actual cost. Now, so the allocative efficiency, ideally, is the minimum cost over the actual cost, and then you have times the distance function. Okay, let's call it distance function. Now, this distance function is actually the reciprocal of the technical efficiency. Is a reciprocal of the technical efficiency. Now, this part here is the cost efficiency. Do you know that? Do you know that?
Yes, please.
So it means that the allocative efficiency, okay, will be equal to the cost efficiency times the distance function, I. That is what it means, okay? But if we are to bring technical efficiency into it, because it's a reciprocal of the technical efficiency, then we are going to have something like allocative efficiency, okay, equal to more or less the CE over D, over technical efficiency. Because the D here is a distance function. The D itself is equal to 1 over T, the technical efficiency. And so if we are to make it technical, that is how it becomes. And so when you cross multiply, you will now appreciate that the cost efficiency is allocative times the technical. Now, this principle is very important. Okay, I want you to understand something here at this stage. I want you to pay attention here. That technical efficiency is a Farrell definition. It's according to Farrell, 1957. And distance function, okay, sometimes we call it D, sometimes we call it DF. Distance function is Shepard. Okay, it's another author called Shepard. Sometimes we call it Shepard distance function. Now, there is a connection between the two. Okay, there's a connection between the two, and the connection is that one is a reciprocal of the other. So technical efficiency is always 1 over D, the distance function, and D is always 1 over technical efficiency. And I want you to understand this because we are going to be shifted into distance function as we do this current work, okay, as we do the cost productivity as we go on. And the whole idea is that, so let's say that I tell you that something is a reciprocal of the other. If the only way to change it is bringing one on top and taking one down. So if I tell you that this one, let me just tell you something like A and B. When I tell you that A divided by B, okay, I'll give you a ratio that A divided by B, and let's call it M. This A divided by B, and I tell you that this is inefficiency. So I want you to make a distance function. What will it be? Who can raise hand and tell me? What will it be? Chris?
It would be B over A.
Exactly. It will be B over A. So you just need to understand that the distance function, which is D, is always the reciprocal of the technical efficiency. And the technical efficiency is always the reciprocal of that. But whenever you decide to use one, then make sure you stick with that throughout. Make sure you stick with that throughout. Okay, unless you decide not to use that one. Okay, any question on this? So you can see clearly that the definition we had, these were the variables for it. Okay. And in terms of time, if we bring time into the picture, this is how I would have defined the technical efficiency. So all that I told you is what is here. That distance function, which is D, which is dealing with Y and X. You can bring the X first. Bring the Y second. The T superscript. The T superscript are all indicative of time, the current year. If I had T plus 1, it would indicate the next year. So don't worry much. For now, you can assume that there's no T there. Okay. So this is the input distance function. This is the input distance function. And it is the input orientation version of the technical efficiency. So the input distance function is a reciprocal of the input oriented technical efficiency. And the output distance function is a reciprocal of the output oriented technical efficiency. And this input distance function, okay, you see the I, it implies input orientation because cost function and input distance function can be related by duality. And this is a principle. In fact, again, what I wrote here is what you see here, the reciprocal duality principle. The principle of duality is what we are using to establish technical efficiency. And then when we go to the graph, you see this. Don't worry, when we go to the graph, you get a picture of all this. So this is technical efficiency, and this is distance function. Okay. If allocative efficiency is 1, we know what it is. If it is 1, then it means that the cost efficiency is the same as the technical efficiency. Do you all agree with that? Because remember, cost efficiency is technical times allocative. So if allocative is 1, then it means that for cost efficiency to be 1, the technical efficiency must be 1. That's the simple principle that you are seeing. Now, another author came in some time later, in 2002, and modified the original Fair et al. Model. And this is how he modified it. Now, if you can remember the Fair et al. One, okay, let me just go back. If you can remember the Fair et al. One, what value was here? The X bar I naught, what was the value? What was the variable there? It was W I naught and X I naught. So there was no X bar. And here you can see that, there is no W. There is no W. And the X has been barred, which means that we are talking about some mean values here. And so you want to take note of that first. The second thing you want to take note is that if you look at the constraints, it's the same as the original one, but the X's have been barred. So you've given them a bar, but not the Y. Remember, we are dealing with cost. So it's the X that we are giving them a bar. Okay. So the X have been given a bar, not the Y. Even the right-hand side, which deals with the DMU undervaluation, is only the X that has been given them. What is the essence of this tone model? It's a long story, but I'll give you a fair idea. The X bar is the W times X. But in this context, the W is the price of the input at that particular DMU. Now, if you look at it, we are not writing. So by the time I talk about a particular input, so the bar here means that by the time I talk about the input, I'm not talking about just the input. I'm talking about the value of the input. not the nominal value, but the real value of the input. So when you look at the W and the X, they are nominal terms. Okay. So the X here that you are seeing it can be anything. It can be, for example, if I tell you a human being, okay, lecturer, and I tell you another human being, cleaner, you will know that you will consider all of them as individual human beings. But in terms of value of this to the university, you will agree that the lecturer will be of more value to that. So because we are not talking about value, we will now assign the values to them. When I mention a lecturer, I am mentioning a lecturer with a value in mind. Do you guys get it? And when I talk about a cleaner, I'm also talking about a cleaner with value in it. So in this case, you will not consider them as the same individuals because there's value attached there. You want to understand this. And this is going to help us to know why did tone bring about this new cost efficiency. Simple. The DMUs in real life do not operate under perfect market, as Farrell and Fair et al. 1985 have said. Okay? They don't operate in a perfect market. They operate in an imperfect market. So if they operate in an imperfect market, the original idea that prices are perfectly determined, horizontally determined, okay, and that the forces of demand and supply affect the price. There's one price for all. Firms are price takers. All of these things don't hold. Input prices are not equal. Okay, and they are exogenous. They are not homogeneous. So what Tone did is that Tone's measure was given by the ratio of the minimum cost value, not just the minimum cost, but the minimum cost value, okay, which you will get from this equation. That's why you have the X bar, the minimum cost value. Value is important. Okay, minimum cost value divided by the actual costs. So when you look at this definition, you will see that the X's are having a bar. But when you look at it, the actual cost is maintaining what it is. The actual cost is maintaining what it is, but the minimum cost has changed. It is the minimum cost. It is the minimum cost that is changing in the Tone model. And you will come to learn now later that the Tone model, the minimum cost is for all firms. Keep that in mind. Keep that in mind. The Tone model, the minimum cost is the minimum cost for all firms in the industry. And in the Farrell model, the minimum cost is the minimum cost at the firm level. When we come with the real examples, you'll understand. The minimum cost at the firm level. Okay. So the Tone cost efficiency shows the differential between the cost actually paid and the estimate of the minimum cost, which is based on values. Okay. Now, why the Tone? We've already mentioned, because of marketing perfection. That's one key one. Firms are price takers, no longer hold. Okay. And then we also indicate that it's limited under marketing perfection. We've said that. It assumes that the inputs are homogeneous when in reality they are not homogeneous. Look at lecturers. Even among lecturers, you have heterogeneity. You have some who are professors, some who are not professors. So there's a lot of heterogeneity for the inputs. It also assumes that there's perfect information. Well, in real life, there's no perfect information. Information is not perfect. If information was perfect, it would have been clear to Donald Trump whether he had lost or he had not lost. In real life, firms are not homogeneous. They are heterogeneous. You made that point. Also, firms face ex-ante price uncertainty. Okay, we don't know the exact prices when they are deciding their production plans. Things can change. You can bring things to the market and nobody will buy the price. So that shows clearly that they didn't know, and so prices are not perfect. Even when prices inputs are homogeneous in real life, the cost efficiency reflects only input efficiencies. If you look at it, but So it's looking at only input efficiencies and not price inefficiencies. And when we talk about price inefficiencies, we are talking about deviation from the competitive market. Another Professor Kamaho and Dyson, they saw this problem, okay, and so they modeled their own separately. You will not do that. The third reason why tone cost efficiency was needed was that the inputs and the output prices were artificially structured. And so they represent the average rather than the marginals. So because of all this, okay, managers decide at the margin using average and for efficiency analysis. And so that can affect the. So what did Tone do? Because of those problems, Tone decided to propose a new scheme of evaluating cost efficiency. In fact, he did the same thing for revenue efficiency. He did the same thing for profit efficiency as well. And look at how he put it in his argument. He said that if two firms have the same amount of input, the same amount of output, and one has a cost of input twice than the other. So firm A has cost twice than B, then the two firms must have the same overall cost efficiency. Okay, one has unit cost of input twice the other. But when you go into the Farrell one, you will still realize that they have the same cost efficiency, the same allocative efficiency. Why is that so? Why is it that your unit cost is twice mine? So then it means I must be more efficient than you. But then the fair et al. Computation will still ensure that they all have the same cost efficiency. And this is where Tone didn't answer. That's how he toasted the problem. So under Tone's own, okay, firms are assessed in cost terms when prices are different, and also when the inputs are not homogeneous. And his new measure of cost efficiency, the firms whose input prices differ will return a different cost efficiency. It's not going to be the same as the fair one. They will give you a different cost efficiency, like the fair Farrell or the fair that assumes homogeneity, and therefore the DMUs with different prices can even give the same cost efficiency. So there are two kinds of cost efficiencies here. The Tone's cost efficiency, okay, and then the Farrell or fair cost efficiency. And the one that we will deal with, we'll do both. We'll do both using this data set. Let me see whether that is a data set that I use.